global demand for soft magnetic composites is expanding at an 8.2% compound annual growth rate. This trajectory will push demand to nearly 50,000 metric tons by 2027. Conversely, upstream carbonyl iron powder capacity is contracting. Strict environmental regulations on carbon monoxide-intensive chemical processing are forcing plant shutdowns in Europe and China. By late 2026, this divergence will yield a 15% structural deficit. This supply gap threatens the production of high-frequency inductors critical for electric vehicle traction inverters. The supply chain for high-purity carbonyl iron powder is highly consolidated. China and Germany control a combined 87% of global synthesis capacity. The United States and Japan hold highly vulnerable positions. Each nation accounts for only 5% of global output. This concentration leaves Western advanced electronics supply chains heavily dependent on imports. Furthermore, European environmental regulations limit capacity expansions in Germany. This shifts production expansion pressure entirely to Chinese facilities. The bottleneck is compounded by the physical non-substitutability of carbonyl iron powder. At high operating frequencies, conventional laminated silicon steel experiences catastrophic eddy current losses. These losses soar to over 5,000 watts per kilogram at 1 megahertz. While manganese-zinc ferrites offer lower losses, their low magnetic saturation limits their use in high-power applications. Consequently, soft magnetic composites made from carbonyl iron powder remain the only viable material for next-generation electric vehicle inverters. The port of Lazaro, Cardenas, has transitioned into a critical Pacific gateway for North American supply chains. Shippers routing cargo away from congested U.S. West Coast ports have pushed annualized throughput to 2.2 million 20-foot equivalent units. This rapid volume influx has overwhelmed the port's physical infrastructure. Average container dwell times spiked from 3.5 days to 7.2 days in the second half of 2025. The sudden doubling of dwell times indicates that the port's internal rail yards have reached structural saturation. The physical footprint cannot clear containers as fast as ocean carriers discharge them. The bottleneck at the port propagates directly into the inland rail corridor. Northbound rail volume through the Lerdo Gateway surged 25% over 2 years, pushing the single-line network to its absolute capacity limit. This surge has paralyzed customs processing at the Texas border. Average border crossing delays escalated from under 4 hours to nearly 15 hours by late 2025. To bypass these cascading rail delays, logistics operators are diverting high-value cargo to long-haul trucking. This modal shift now accounts for 26% of shipments, forcing shippers to absorb an additional $30 to $40 per ton in transport premiums. Primary aluminum production depends entirely on synthetic cryolite to lower smelting temperatures. Without this chemical flux, the Hall-Héroult process cannot operate. Chinese exports of synthetic cryolite fell by over 35% between 2021 and 2024. This contraction is driven by domestic environmental restrictions on fluorine-containing chemical plants. Consequently, European smelters have drawn down strategic inventories to just 25 days of operational reserve. This level breaches the historical safety threshold and exposes the continent to immediate supply disruptions. The root cause of this shortage is a structural squeeze on hydrofluoric acid precursors. Synthetic cryolite manufacturers are losing a bidding war against higher-margin industries. Ultra-high-purity hydrofluoric acid consumption by semiconductor fabrication plants is growing at over 15% annually. This surge has bid up acid-grade fluorspar spot prices by 48% since late 2022. As a result, the share of global hydrofluoric acid allocated to synthetic cryolite will contract to just 12.5% by 2026. High-margin electronics manufacturing is effectively pricing out heavy metallurgy. Smelter operators cannot easily adapt to this deficit. Altering the chemical bath ratio to conserve cryolite triggers severe thermodynamic penalties. Reducing the sodium fluoride to aluminum fluoride molar ratio from 2.70 to 1.80 drops alumina solubility to a critical 2.2%. This drop causes localized voltage spikes and severe anode effects. If the ratio falls further to 1.50, energy consumption surges by 25%. Operating in this regime reduces the thermal safety margin to less than 15 degrees, risking a catastrophic cell freeze-out that permanently destroys the equipment. North American semiconductor manufacturing faces a critical supply bottleneck in ultra-high purity nitric acid. By 2027, domestic demand will reach 27,000 metric tons. However, domestic purification capacity is projected to reach only 16,200 metric tons. This mismatch creates a 40% structural deficit. The deficit is driven by the transition to gate-all-around transistor architectures. This shift increases wet cleaning steps by 35%, accelerating chemical consumption. Advanced node fabrication requires unprecedented chemical purity. At the 2-nanometer node, maximum allowable metal impurities drop to just 0.5 parts per trillion. This threshold requires multi-stage quartz distillation to eliminate transition metals. Simultaneously, process complexity is escalating. Wet cleaning steps rise from 125 at 7 nanometers to 210 at 2 nanometers. This increases average nitric acid consumption per wafer, start to 4.5 liters. This chemical cannot be easily transported over long distances. Nitric acid is highly corrosive and leaches trace metals from container walls during transit. In standard high-density polyethylene containers, impurities exceed the critical 1.0 parts per trillion threshold in just 2 days. Specialized fluoropolymer-lined containers extend this window to only 10 days. This rapid degradation prevents transoceanic shipping. Purification facilities must be built directly adjacent to domestic semiconductor fabrication clusters to avoid supply chain failure. The Australian East Coast gas market faces a severe geographic mismatch. Rapidly depleting legacy reserves in the southern Gippsland Basin cannot meet winter demand in Victoria and New South Wales. This regional deficit is projected to reach 180 terajoules per day by 2026. This represents a 300% increase in the supply gap over 5 years. The Northern Gas Pipeline cannot mitigate this shortfall. Its physical throughput has flatlined at a hard ceiling of 90 terajoules per day since 2024. Consequently, winter spot prices are projected to rise to 17.5 Australian dollars per gigajoule by 2026. The physical limit of the pipeline acts as a direct transmission mechanism for economic friction. Unlocking the Beetaloo Basin's vast reserves requires massive capital expenditure and time. Scaling the pipeline to 700 terajoules per day requires 1.2 billion Australian dollars. This expansion carries a rigid 36-month construction timeline. This lag leaves the southern states exposed to structural winter deficits until at least late 2028. Interim compression upgrades offer a faster alternative. For 150 million Australian dollars, capacity can double to 180 terajoules per day within 12 months. However, this stopgap measure is insufficient. By the time these upgrades are complete, the projected winter deficit will already outstrip the new capacity, leaving industrial users vulnerable to curtailment. Tellurium is a highly chalcophile element with an extremely low crustal abundance. It is not mined as a primary commodity. Instead, it is recovered almost exclusively as a minor byproduct of copper anode slime refining. This metallurgical dependency makes the global supply of tellurium highly inelastic. While copper refining yields only 1 metric ton of tellurium per 350 metric tons of copper, demand for high-purity optical applications is expanding. High-purity feedstock demand grew at a 23.1% compound annual rate from 2020 to 2025. This mismatch has driven spot prices for 6N tellurium up by 68% over a 24-month period ending in late 2025. Downstream crystal growth physics compounds the upstream material bottleneck. Manufacturing Acousto-Optic modulators requires paratellurate single crystals grown via the Czochralski method. This process requires a minimum feedstock purity of 6N to prevent thermal lensing under high laser power. Growing a single ingot takes up to 28 days of continuous thermal stabilization. Even under optimal conditions, usable crystal yields average just 38.5%. Lower-grade feedstocks cause lattice dislocations and structural cracking, dropping yields below 25% and rendering them economically non-viable. This highly constrained supply chain is colliding with surging demand from advanced technology sectors. Acousto-optic modulators are critical for laser printed circuit board drilling and semiconductor lithography. The transition to sub-7 nanometer nodes and advanced packaging has accelerated demand. Laser drilling applications alone expanded 30% in 2024. The total addressable market for these modulators has expanded from 5,190 units in 2021 to 12,330 units in 2025. With tellurium supply locked to copper mining rates, this demand surge is pushing the optical manufacturing sector toward a structural breaking point. South Africa's primary coal export corridor is in a state of structural collapse. Rail deliveries to the Richards Bay Coal Terminal contracted by 38.3% between 2017 and 2024. This decline left over 43 million tons of terminal capacity unutilized by rail. To prevent a total export shutdown, mining operations initiated an inefficient road arbitrage strategy. Road-hauled coal deliveries surged from 0.5 million tons to 12.5 million tons over the same period. This represents a 2,400% increase in road freight dependency. Despite this massive trucking mobilization, total exports remain severely capped. Annual throughput has failed to breach 60 million tons since 2021. The resulting structural export deficit exceeds 30 million tons relative to nominal terminal capacity. The transition from rail to road imposes a severe microeconomic penalty. By 2024, road transport costs escalated to $55 per ton. This creates a $39.20 per ton premium over standard rail tariffs. This cost premium severely erodes the netback margins of landlocked coal producers. To sustain these volumes, daily truck deployments along the N2 highway corridor scaled from 40 to over 430. This heavy traffic causes rapid degradation of municipal road infrastructure. The root cause of this logistical shift is systemic infrastructure failure. Cable theft incidents on the rail network peaked at over 4,500 in 2022. Ongoing security deficits prevent any meaningful recovery of heavy-haul rail operations. Supercritical carbon dioxide power cycles operate above the thermodynamic critical point of 31.1 degrees Celsius and 7.39 megapascals. At this state, the working fluid exhibits the density of a liquid and the viscosity of a gas. This dual state reduces compression work and enables thermoelectrical efficiencies exceeding 50%. The high fluid density allows a massive reduction in turbomachinery size. A closed-loop supercritical carbon dioxide Brayton cycle requires a physical footprint of just 3.8 cubic meters. This represents a 91.5% reduction compared to conventional subcritical steam systems. This compact footprint allows a 10-megawatt electrical turbomachinery unit to be skid-mounted. Civil engineering and structural requirements are drastically reduced. However, these thermodynamic advantages are bound to extreme operational parameters. The transition to utility-scale installations is bottlenecked by specialized manufacturing capacity. Primary heat exchangers must be printed circuit heat exchangers manufactured via high-pressure solid-state diffusion bonding. A structural deficit in global diffusion bonding capacity is projected to emerge by late 2026. By 2030, this capacity gap will widen to 273.3%. Only a limited number of specialized facilities globally possess the required high-pressure presses. This physical constraint prevents the scaling of pilot plants to utility-grade installations. Simultaneously, the raw material cost premium for Inconel 740H is rising. This premium is modeled to reach $205 per kilogram by 2030. The supply chain for high-purity nickel superalloy forging remains highly inelastic. The physical footprint savings of supercritical carbon dioxide are currently offset by extreme material costs. While the technology reduces civil and structural costs by 75%, primary heat exchanger costs surge. These heat exchangers require $38.5 million, representing a 156.7% increase over steam systems. High-pressure piping and valves also demand a substantial premium. They must safely handle 25 megapascals of pressure at temperatures exceeding 700 degrees Celsius. This requirement drives piping costs to $18 million. Consequently, total power block capital expenditure for a 100-megawatt plant stands at $85 million. This represents a 13.3% premium over conventional steam. The engineering challenge has shifted entirely from thermodynamic design to advanced metallurgy economics.